To Jamel Jaber from University of Carthage, and he will speak about questions on Banach lattices, algebra. Sorry.
Thank you.
Yes.
Thank you. I will start by thanking the organizing committee. Today, I will speak about Banach lattice algebra and discuss some questions on this class of algebra. So we begin by the definition. A Banach lattice algebra is at the same time is a Banach lattice. It's at the same time is a Banach lattice, which means that is a vector lattice with a Arens norm, which is complete, together with an algebra with a submultiplicative norm, and with the positive cone is closed under product. Here are some examples of Banach lattice algebra, and we see here that in Banach lattice algebra we have many structures. We have topological structure, we have an order structure, and algebraic structure. Though so many questions can be stated here. In 27, Wicksteed published 2 papers on which he asked many questions. Most of these questions are come from the Banach algebra theory. I see here some of these questions. The first question about the utilization of Banach lattice algebra, to say if we can add a unit element to a given Banach lattice algebra. For the second problem is about the existence of positive approximate unit, which means that if we have a Banach lattice algebra with an approximate unit, can we find a positive approximate unit? For third problem is about how to develop a tensor product in the category of Banach lattice algebra. Another problem is about the Arens regularity of Banach lattice algebra. Today, I will speak about the third and the fourth problem, about the problem of the tensor product and the Arens regularity. So we start with the third problem. As we see here, the question is, the category, the tensor product of Banach lattice and the tensor product of Banach algebra are well developed. And what we can say about the tensor product of Banach lattice algebra, if we can define in this category a tensor product with universal property with respect to the operation in Banach lattice algebra. So we will start by some definition. A linear operator T between 2 vector lattices is said to be lattice homomorphism is to respect the absolute value, and I believe the bilinear map B is called a lattice bimorphism if the absolute value of B of x, y equal to B of value x, value y for all x, y in A cross B. In his fundamental paper, Fremlin defined a new vector lattice, which is the tensor product for a given vector lattices I, A, and B, with a lattice bimorphism operation, which is the tensor, with this universal property. Let's say that for every lattice bimorphism B from A cross B to any vector lattice C, then B can be written as the composition of T with the tensor operation. If we want to work in this space, in this vector lattices, we only can use this universal property with maybe 2 additional property. The first is an order dense property, which said that the algebraic tensor product is order dense in the Fremlin tensor product. That is, if we have for every element u in the Fremlin tensor product, we can find elementary tensor product positive, which is less or equal to u. The second is a boundless property, that is the algebraic tensor product is majorizing in this in the Fremlin tensor product, which means that for every vector in the tensor product, the Fremlin tensor product, we can find a positive elementary tensor A, tensor B, such that the absolute value of U is less or equal to A tensor B. Here we see some example of construction of this, the Fremlin tensor product. I see Fremlin, Grobler, and Labuschagne, Wicksteed, and de Bachter, Schaefer. So here we give some examples of how we use the Fremlin tensor product to transfer some results from linear operator to bilinear maps. The first theorem, which is well known in the operator theory, says that if we have a positive bilinear map B from A1 cross B1 into the complete vector lattice C, and where I1 and B1 are majorizing in vector lattices A and B, we can extend B to the whole space A cross B. That's to say that the set of all positive extension is a non-void convex set, and moreover, his extremal points are lattice bimorphism whenever B is a lattice bimorphism. The second result is the Cotedolazzi characterization of lattice homomorphism, and we can get the same for bilinear map. That is to say that positive bilinear map B from A cross B into C, where C is the incomplete vector lattice. A positive bilinear map is a lattice bimorphism if only if for every bilinear map P, which is equal less or equal to B, then can be written as the composition with an orthomorphism on C. So I will speak a few words about the tensor product of lattice order algebra. So if we have two lattice order algebra A and B, and we have now the Fremlin tensor product, the algebraic tensor product A tensor B is a vector subspace of the Fremlin tensor product, but now the algebraic tensor product is furnished by a natural multiplication. Then we have here an algebra, which is a vector subspace of the Fremlin tensor product. And here the question is, can the Fremlin tensor product can be furnished with multiplication such that the Fremlin tensor product is an order lattice algebra? This question, as it's stated here, is seems difficult for the class of lattice order algebra. So we will discuss this question in an important class of lattice order algebra, which are the f-algebra, which is the f-algebra. We recall the definition of an f-algebra and some examples, and the most of the functional algebra are satisfy this condition. To start to discuss this question in the class of f-algebra, I will start by the typical example of f-algebra, which is the safe X case. Now, It is well known that the Fremlin tensor product of C of x and C of y is the vector sublattice generated by the algebraic tensor product of C of x and C of y in the f-algebra C of x cross y. And we see here that we have here C of x cross y is an f-algebra. C of x tensor C of y is an algebra, and we take the vector sublattice, which means we take the closure of this algebra by the lattice operation. So to give an answer for the C of x case, we have another question: is does the vector sublattice generated by an algebra, which is here C of x tensor of C of y, is again a subalgebra? This question is discussed by Eriksen and Isbell in the case of f ring, and he gives a positive answer. In the case of f algebra, we have again a positive answer, which means that if we have A and an f algebra and B subalgebra of A, then the vector sublattice generated by the algebra is again an f algebra. So if we apply this result to C of x case, we have C of x, the Fremlin tensor product of C of x and C of y is an f algebra, which contain the algebraic tensor product. So in the general case of f algebra, we have this theorem with this result, which said that the Fremlin tensor product of two f algebra is again an f algebra. Now we have a multiplicative universal property, which that says that if we have a lattice bimorphism B, which is multiplicative, then there exists an algebra and lattice homomorphism T, such that B is the composition of T and the tensor. Now we speak about tensor product of Banach lattices. We recall here that if we have A and B are Banach lattices, and I tensor B their Fremlin tensor product, we want to put here a topological norm in the tensor product, in the Fremlin tensor product. Then a cross norm in the Fremlin tensor product is said, a norm is said to be a cross norm if satisfy this condition. And Fremlin defined the positive projective tensor norm given by this formula, and he should prove that the Fremlin tensor product with respect to this norm, the positive projective tensor norm, is now a normed vector lattices, and the positive projective norm is the greatest cross norm which satisfy this condition. So if we take now the completion, we get a Banach lattices, which called Fremlin projective tensor product. And we have this result that if A and B are Banach lattices, then the Fremlin projective tensor product now is a Banach lattice with this universal property. That is, for any Banach lattice C, for any bilinear map B from A cross B into C, there exists a linear map T, which in such manner B is the composition of T with the lattice bimorphism tensor. And we have T is a lattice homomorphism if only if B is T is lattice homomorphism if only if B is lattice bimorphism. Moreover, we have this properties, and there is property that is the algebraic tensor product is dense in the Fremlin tensor product, in the Fremlin projective tensor product. Here we give some application. It will be used in the second part of my talk. If we recall that if the set of all regular operator from E into F, where E is Banach lattice and F is the complete Banach lattices, is a Banach lattice with respect to the R norm, which we defined by the norm R of T is the operator norm of the absolute value of T. Now, if A and B are Banach lattices, and B prime is a topological dual of B, we can show that the space of all regular operator from A into B prime is exactly the dual of the Fremlin projective tensor product. To see this, just if we take T positive operator, and we can define this bilinear map, and bilinearization, they give rises to a linear function in the positive projective tensor product with Z formula. And we can show that this is a lattice and norm isomorphism. Now we discuss our problem is about the tensor product of Banach lattice algebra. So if we have now a Banach lattice algebra, A and B Banach lattice algebra, and we have their Fremlin projective tensor product, we want to see if the Fremlin positive projective tensor product can be endowed with a multiplication in such manner this space is become Banach lattice algebra. So the question is, does the Fremlin positive projective tensor product has a Banach lattice algebra structure? So in the case of C of X and C of Y, that is trivial because the Fremlin tensor product of C of X and C of Y is the C of X cross Y, which is a Banach lattice algebra. In the general case, we have this result that if A and B be Banach lattice algebra, then their tensor product, the Fremlin projective tensor product, is a Banach lattice algebra. We can put here multiplication such that this is begin Banach lattice algebra, and we have the multiplicative universal property, which says that every now multiplicative bilinear map phi, there we can find a positive algebra homomorphism, which is such that phi is the composition of T with the tensor, the bimorphism tensor. To construct, now we will see how to construct a product in the Fremlin projective tensor product. First, if we take element positive A and B here, we define the bilinear map from I cross B to the projective space by this formula. LAB of XY is A tensor B point X tensor Y, and using the universal property, we get a positive operator lambda AB by this formula, and we see that lambda AB of vector U here is the multiplication of A tensor B by U. And for second step is if we take any element A and B, and we can decompose LAB in such manner, and we get again bilinearization lambda AB such that lambda AB of any element of any vector here in the projective space lambda AB of U is the multiplication of U by A tensor B. And finally, for all element V in the Fremlin tensor product, in the projective tensor product, we define this bilinear map by this formula, and using again the universal property to obtain this multiplication. U star V is by this formula, and we can prove using the density of the algebraic tensor product that the norm, projective norm, is submultiplicative with respect to this product. So here we can extend the multiplicative universal property, which is satisfied for the positive bilinear map, to extend this property to regular bilinear map. Regular bilinear map is the difference of two positive bilinear map. So here this is the multiplicative universal property, which is satisfied for all regular multiplicative bilinear map. For the second property is the connection between the projective tensor product of the two Banach algebra IB and the Fremlin positive projective tensor product of the Banach lattice algebra A and B. Now we will discuss the problem of the approximate unit. Here we recall that in a Banach algebra, in net E lambda is said to be bounded approximate unit if it is bounded, and A E lambda converges to A, and A lambda for A converges to A, and this bounded approximate unit is said to be positive. It is composed by positive elements. And so we have this problem, this question is for a given Banach lattice algebra, does the following statement are equivalent? If we suppose that both of A and B has bounded approximate unit, and the connection between both A and B has bounded approximate unit, and the Fremlin projective tensor product has a bound approximate unit. The first result in this direction is we can show that one implies two. That is, if A and B has bound approximate unit, then the positive projective tensor product has also a bound approximate unit. For the converse, we are enabled to show to give a complete answer for the converse, but if we add an extra condition, which is if A and B are Banach lattice algebra, such that we add here the fact that A and B has non-zero positive multiplicative linear function, that is, the character of A and B are not trivial, then we have the converse, which means that if the projective tensor product have a bound approximate unit, then A and B have a bound approximate unit. To see the proof of the first result, if we pick an approximate unit of A and approximate unit of B, then it is easy to see that this net is an approximate unit of the positive projective tensor product. We see here that using the fact that the projective norm is a cross norm, that this net is bounded, and we can see that if we multiply this net by x tensor y, and using the submultiplicative property of the projective project norm, that this converges to 0. And then by linearity, we can show that this is true for all u in the algebraic tensor product. So using now the density of the density of the algebraic tensor product in the Fremlin and the positive projective tensor product, we can get the result. For the proof of the second result, if we suppose now that we have an approximate unit of the projective tensor product, and we pick two characters f and g, we can define a bilinear map using f and g by this formula. And using the universal property, we can define this positive operator with this formula, and we can pick now for each lambda we have h tensor of u lambda equal to a lambda b lambda, and we can prove now that e lambda is an approximate unit of a, and the same for b lambda. To see this, just we will use the continuity of h tensor, as we write g of b a point a lambda minus g of b a that converges to 0, and we pick simply element b such g of b equal to 1 to get the result that e lambda is an approximate unit in A, and the same we can do for the b lambda. So I will finish this part by the projective tensor product of Banach f-algebra. Now, if we take two Banach f-algebra, what we can say about their tensor product, their positive tensor product. In the case of C of x of C of y, this is true because here we have Banach f-algebra. Then the tensor product of two Banach f-algebra is again f-algebra in the case of C of x. In the general case, if we pick A and B two Banach f-algebra, then we know that the Fremlin tensor product is an f-algebra, and it is normed by the positive projective norm. So we need this lemma, which say that if we have a normed f-algebra, then the completion of E is a Banach f-algebra. And using this lemma, we can prove that if A and B, we can prove that the positive projective tensor product of two Banach f-algebra is again an F subalgebra. So the second part in my talk, I will speak about the Arens regularity of Banach lattice algebra. For a given normed algebra or lattice order algebra A, we have A, we can see A as a vector subspace of its bidual by the canonical embedding. And since A has an algebra structure, we want to pick in the B dual an algebra structure in such manner P is an algebra homomorphism. That is to say, we want to pick a product in the B dual which extend the initial one in A. Arens defined two products in the dual of an algebra. The two products are defined by steps. The first step, if we pick an element A on A and functional in A, we define two linear functions, f point A and f star A, defined by this formula. The second step, if we have an element f in the dual and grid f in the B dual, we can define two functions on A by this formula, f point f and f star f. And finally, if we have two elements in the B dual, we define the first Arens product by this formula, f point g of f is equal to f g point f, and the second Arens product by this formula again. Now, with respect the first Arens product or the second Arens product, the B dual of normed algebra is now a Banach f-algebra. And we can see that if f or g are in A, then f point g is equal to f star g. That is the two product coincides if one of the factor is in A. In particular, if the first and the second Arens product coincide in A, but in general they not coincide in the whole B dual. So we have the definition. The algebra A is said to be Arens regular if the two product coincide in the whole of the bidual. Many works in this problem, the problem of Arens regularity, in the case of Banach algebra or lattice order algebra, we see it here some examples that almost f-algebra in particular or f-algebra are Arens regular. Also, all C-star algebra are Arens regular. Now, this is a characterization for the Arens regularity. If we have a Banach algebra, then A is Arens regular if only if for each functional f in A, this linear is weakly compact. And this is equivalent to, for a given bound sequence xn and yn, we have the iterated limit are equal whenever they exist. So in the case of, if we want to discuss the case of Arens regularity in Banach lattice algebra, I will start by this example, example L1, which is a Banach lattice algebra with the pointwise multiplication. This Banach lattice algebra is Arens regular simply because it is an f-algebra. So but if we put the convolution product, the Banach lattice algebra L1 with the convolution product is again a Banach lattice algebra, which is commutative, which has an element, a unit element, but is not regular. To see this, we pick this functional in L1, h in L linear function in L1 defined by h of 0 is equal to 1 and h of n is equal to 0. And for we define the two sequence x1, xn, and yn defined by this formula. And an easy computation show that this limit, the two limits are different, and so L1 is not regular. It's not Arens regular. So there is we see here some results in this direction. That the first result says that if we have a Banach lattice algebra, if L1 is embedded as an algebra in A, that A is not Arens regular. The second theorem give a characterization of this algebra where, if we can put embedded L1 in A, we would say that if A is a Banach lattice algebra, then L1 is embedded in A as an algebra, if only if there exists a sequence of this form, which is bound disjoint sequence and not converges weakly to 0. The final result in this direction is the connection between the Arens regularity of A and B and their Fremlin projective tensor product. And we can show this result that if A-B are Banach lattice algebra, such that the multiplication is not trivial, then if the positive projective tensor product is Arens regular, then A and B are so Arens regular. Thank you for the time.
So thank you very much. Any questions?
I have a question. Yeah, come on. So you are speaking about approximate unit in Banach lattice, and I think that is slide 30. So, and we take nets. Why did you take nets if I think that the convergence is a norm convergence and all things are in norms? So why didn't you work within sequences and no, before, a little bit before, sorry. A little bit before. Oh. Thank you. Oh.
Oui. Oui. This is the definition of approximate. I think that this is more general. We work as usual with the net, but not with the sequence. Okay.
I think we can find a net, but not a sequence. For example, if you take L1 with uncountable support, so we can find a net, but not a sequence. So because here the convergence for every x, there is a convergence. It's not the convergence of the net itself. So it's for every x. So it's needed here.
Just a quick comment about this. I mean, the convergence is, if you multiply things, you should think of it that it converges in a strong operator topology to the identity operator. This is how you can think of it. So you're not really working with norm convergence, but strong operator topology convergence. And this is why you need nets. I think that's the easiest way to explain this. Anyway, I had another quick comment also related to this, because I think your proof shows a little bit more actually. Because there's also this notion of a bounded right approximate unit and a bounded left approximate unit. And the proof that you showed actually shows that if you start with two bounded left approximate units, then the tensor product becomes bounded left approximate units, and the same way for the right. So actually your proof shows a little bit more than what you have said. It shows that if you start with two bounded left approximate units of A and B, then the tensor product is going to become a bounded left approximate unit of the tensor product. And the same for the right. So that's a little bit stronger because yeah, you just have a little bit stronger. You also have a result for both left and right approximate units. And if you combine them, you get the result that you already. That was just a comment that I wanted to make.
Any other question or comment? Okay, let's thank the speaker again. Okay, so we will begin in 10 minutes. Okay.